Hey y'all, my name is Jeff Carlisle. I'm an 8th grade science teacher based in Austin, Texas, and I'm excited to walk you through Amplify's Evolutionary History unit. The big question that this unit drives towards is, why do species, both living and extinct, share similarities and also have differences? Students learn about how scientists compare similarities in body structures from organisms unearthed through excavation. By tracing the development of body structures throughout the fossil record, scientists can definitively prove how all organisms share a common ancestry and can determine how closely related different species are. Before we begin, make sure you've read and annotated the unit overview, unit at a glance, and standards, as well as the science background knowledge. Grab a pen and your unit internalization guide, and we're ready to begin. Now, just like your students like to ask, why does this matter? So the reason why this unit matters is because it immerses students into some of the big ideas in science. How did we get here? About how the Earth is a dynamic and ever-changing system, about how the traits that we have were developed over millions of years through natural selection, about how every organism has a common ancestor, and about how we can use a robust system of evidence and reasoning to prove how evolution not only led to the species that exist today, but also how it's an ongoing system and will continue to change life in perpetuity. The anchor phenomenon that grounds this unit is the discovery of a new fossil in Pakistan. In their role as a paleontologist, students are tasked with determining the mystery fossil's evolutionary history so they can accurately place the specimen in a museum exhibit, particularly if it's more closely related to whales or wolves. Chapter 1 focuses on the question, why do different species share similar structures? Students watch a video that shows the fossil being discovered and brought to the museum. And they read an article that illuminates the many similarities that we share with blue whales, the largest living organisms on Earth, particularly things like body structures. Students then get the chance to dive into the simulation, which allows students to navigate through an evolutionary tree and trace the history of an organism's ancestry. Students also engage in a modeling activity to determine the similar body structures of two descendant species based off of their common ancestor. Through these activities, students internalize Progress Build 1. Body structures shared between species are evidence that these two species inherited the shared structures from a common ancestor population. Chapter 1's focus task requires students to use the modeling tool to analyze similar structures in descendant species in order to predict what the structures of the common ancestor must be, and explain how they arrived at this answer. Pause here and try it on your own. After selecting the appropriate body structures, students are then asked to explain the question, how do you know which structures are present in species A? They should have noted that species A has a nostril backbone, tail, and a back limb because those are shared structures between species B and C. B and C would be descendant species, and they inherited these structures from their common ancestor population, species A. In Chapter 2, students are asked the question, how does an ancestor population evolve into descendant species with differences in their shared structures? And how did descendant species from a common ancestor become very different from one another? Students begin by reading an article titled, Where Do Species Come From? And engage with the natural selection simulation to learn more about how speciation occurs. Next, students use the evolutionary history simulation to investigate the magnitude of structural changes across different lengths of time by examining giraffe ancestors, Elamerix and Acanthostega. Based on the amount of time that has elapsed between each species' appearance in the evolutionary tree, we can see that with longer amounts of time, more dramatic changes occur in the traits. Students eventually reach Progress Build 2 then. Species that share structures can have differences because they have been in separate environments and have changed in different ways over time. In the Chapter 2 focus task, students are asked to show how the body structures of the populations of an organism might change over time due to the environment in which they live. Students are given a model in which they predict how an organism's traits might change due to their environment by identifying the likely skeletal structures of descendant species from the common ancestor. Pause here and try it on your own. After students have made their selections, showing what the different traits are for organisms in environments A and B, they're then asked to answer two questions. How does this model show how species that share a common ancestor can become very different from one another? The key idea here is showing how the environment in which they live can produce different results of the traits. They're then asked to identify what remains stable over time in their model and what changed. They should have noted that the skull and nostril shapes remain stable, and both of them still have backbones. However, the thickness of the backbones and the size of the tail and the limbs have changed. Students, when they get to Chapter 3, are asked the question, when you compare different species, how can you tell which species are more closely related than others? Students begin by modeling evolutionary relationships using Connex pieces. They are given a model evolutionary tree with Connex combinations changing over time. However, some are blank, and students will need to analyze the patterns to predict which structures they would see in the missing tree. Students later are taught how scientists use similar techniques to organize species on an evolutionary tree. Students eventually arrive at Progress Build 3, which states that because populations separate and begin evolving differences at different points in time, similarities and differences in body structures can be used to interpret evolutionary relationships. Chapter 3's focus task then asks students to complete the task of assigning the mystery fossil we saw in the video at the beginning to the correct exhibit. Is it more closely related to a whale or to a wolf? Pause here and try and answer the question on your own. When we arrive at the answer, students can choose either whale or wolf, but are evaluated more so on the quality of the evidence and how it is used to support their claim. For example, if they choose whale, they should have noted that it has a long, pointy jaw, or a nose that's higher on the skull, and teeth that are rounder and more spaced apart. If they instead chose wolf, they should have noted how some of the teeth were pointy and triangular, and the nose is almost at the end of the snout. In Chapter 4, students are presented with a novel scenario that relies on similar skills from Chapters 1 through 3. A new fossil, the Tometti fossil, is being placed in a museum exhibit, but scientists need to determine if it is more closely related to ostriches or crocodiles. Students are presented with images that show structural features in each of the three organisms, such as hollow spaces in the skull. Later, students are presented with evidence cards for each species and their traits, such as skulls and limbs. The culminating activity is a science seminar in which students are asked to conduct a discussion that aims to decide whether the fossil belongs in the crocodile or ostrich exhibit in the museum based on the evidence they analyzed. For the Chapter 4 focus task, students enlist the knowledge they've gained to answer this question. Is the Tometti fossil more closely related to ostriches or to crocodiles? Pause here and try it on your own. Now, as with the previous chapter's task, students are evaluated not on whether they choose the correct exhibit, but rather if they use strong evidence to support their claim. They're also required to address the counterclaim and justify why it's not more closely related to the organism they did not pick. We're going to take a moment and look at some of the items from Progress Builds 1, 2, and 3 in the end of unit assessment, so make sure you have that out and ready. Progress Build 1's question involves a fossilized snake and a rat, and asks, this fossil snake and this living rat both have a structure in their skull called the quadrate bone. What could explain why both species have a quadrate bone? Pause here and try it on your own. If you chose answer C, congratulations, you are correct. As we remember from Progress Build 1, body structures shared between species are evidence that these two species inherited the shared structures from a common ancestor population. The Progress Build 2 question involves a fossilized bird and a salamander and asks students to analyze these two structures. Go ahead and take a moment to read over the question, pause, and answer. If you chose selection A, congratulations, you are correct. As we remember from Progress Build 2, species that share structures can have differences because they have been in separate environments and have changed in different ways over time. Finally, with Progress Build 3, we are presented with three different organisms, a sea lion, a zebra, and a bandicoot. We're given 3 different descriptions of body structures that they have. Take a moment to read the question, the answers, and pause. Now, if you chose answer C, congratulations, you're correct. As we remember from Progress Build 3, because populations separate and begin evolving differences at different points in time, similarities and differences in body structures can be used to interpret evolutionary relationships. For one of the constructed responses, students are then given 3 different organisms: a desert cottontail rabbit, a grizzly bear, and a sea otter, and then the prompt is also seen here on the screen. Take a moment to pause and answer it for yourself. For the constructed response, Amplify's rubric guides you through what we would expect to see from students at different progress builds, but ideally we'd be here. Take a moment to read the Level 3 student response. You can go ahead and pause. And congratulations, you have made it to the end of the Evolutionary History Unit Internalization video. I wish you the best of luck and have a great day.